All right, morning everyone. It's Wednesday. I wonder if we would have had a snow day today. If we actually had school. Just wanted to give you some update on marking period forward, grades, how we're moving forward. Doesn't look like we're going to end distance learning anytime soon. The district has adopted a policy of standards-based gradings versus numerical grades. I would like to say that I'm completely competent to explain that to you, but I really am not. So standards based in my interpretation of what they're saying is basically there's going to be a grade range from what you do is going to determine your ultimate standard that you achieve, at the 5 weeks and end of marking period if we make it through the whole marking period. But one caveat with that, if we do go back to school, then apparently grades come back into play and standards go out the door. We don't know much about this other than what they're saying. So I'm just letting you be as fully informed as possible. So right now, what basically is going to change for us is the only thing is I'm not going to be able to use school tool for grades right now. I'm just going to use it to send in grades at the 5 weeks and 10 weeks if we make it that far. You'll see kind of your feedback grade on Google Classroom. It will not calculate your average correctly. If it even does, I'm not even sure if it does. I will keep a separate grade book, and then that will update your average. So basically, your average that you get from the work that you're doing, if you get to, 90 or higher, you'll get standard 4 or the highest standard, whatever they call it. I forget what they call it. I have to figure out those grade ranges with the other chemistry teachers. We're still working on that, so I can't really tell you, ideally what it is. Probably the top 2 are passing, the bottom 2 are not passing, or it could be the bottom one doesn't pass and then the top 3 are passing. That's some stuff that we have to figure out. We have some meetings to determine and figure that stuff out. So basically, if you can, for most of you, it's just continue what you're doing. You're doing fine. We're just seeing that you're doing work. We're trying to prep you for things. Obviously, we don't have a Regents exam to prep for, but some people are going on to other things. We want to expose you to some different concepts in chemistry. Today, we're going to start a unit called kinetics and equilibrium. I abbreviate it as KEQ. And then we'll go through, you're not going to do everything like we would do it in the classroom. There's some concepts that are probably going to be a challenge to do this way. But we will do as best we can and try to expose you to as much material as possible. New thing, Edpuzzle. I believe some of you are familiar with it. If you are not, you need to become familiar with it. I created classes this morning. So you guys are there. There's an assignment on Classroom. I will also put it in the assignment today. Basically, it's where you would watch videos from. So probably moving forward, I don't know if I'm going to do it on Friday or wait till next week. My daily lessons like this, I'm going to assign through Edpuzzle. It's a way to assure that you are actually watching it and you'll actually get credit for watching it. There'll be some moments in time where you have to stop and answer some questions and click through it. If you've never done that before, it's just kind of a guided, it's like me stopping the video and asking a question is kind of what it is. On there today, there's a quick little, I think it's like 2 minutes on the topic that we're talking about today, which is collision theory. And then that's basically just to see that you guys can do it. Your login information is going to be your Google School login information. I imported all of your school addresses. It basically copied it from Classroom. Apparently, it's going to put a grade onto Classroom too. I want to see how that works. That's going to be a percentage grade. That's not going to be the grade that you're going to get for it. And I don't know how that works on the grading side of it. So we're going to learn that together. But I need you to complete that by Friday. Because I think Friday, I don't know if I'm going to do it Friday or Monday, where my lessons now that I'm doing this way are going to be done through Edpuzzle instead of through YouTube. So you'd have to sign in, do it, answer the questions and things like that. There's some people that aren't doing some things, so we just have to make sure that you're actually doing it. No real different, it's just a different, basically, site that you're going to go through to do it. Okay? All right, your new KEQ packet will be uploaded today. Your homework in it is pages 5 and page 7. Page 1 and I think it's page 2 and 3. It's kind of a notes page. Yeah, it's not anything that I'm going to assign. You could use it to kind of take your notes as we're going through stuff today, if you want. And then there's a video of I didn't spell lycopodium right as I'm looking at it there. There's a video on lycopodium. I'm going to fix that because that's going to bug me. Which is a cool stuff. It explains what it is in the video. It's a cool demo, nice flame stuff. Couldn't do it here in my house. Outside's too cold, so I found a video for it. Okay, so that's just something to watch, see, it's cool, something exploding, or combusting, I should say, not really exploding. All right, so that's that. We'll move into what we're doing here, bell ringer. A reaction, we're gonna be talking about chemical reactions. So last unit was nuclear chem. I believe I put the grades for the tests on Classroom. Thank you for the vast majority of you doing it and doing it correctly. There's still some people that aren't doing any work. There's no way they're going to pass. Brings up the final average calculation, which I don't really know a lot of information for it right now, but the only thing we have numerically is your grades through marking period 3. So I know what your final average is right now if they don't let us do some type of grade numerical calculation for marking period 4. Some people, are good. Some people not so good. You can get the same average by just taking marking period 1, marking period 2, marking period 3, and just doing a straight average of it. That's what it is. All right, you can see on School Tool, I think they release grades Friday. So you can see on School Tool what your marking period 3 grade is, which you should, but some people won't know which one it is because some people I had to go back to March 16th and use that grade. It was a complicated process to figure out marking period 3 grade. But what can you do to make a reaction go quicker? All right, you can increase the temperature. You can make the particle size smaller. All right, so, little smaller reactants. All right, you can use certain types of chemicals. Ionic compounds versus covalent compounds are going to go quicker. All right, so that's a quick little intro into it. And we're going to be talking about speed and rates and stuff like this. This is that video. I'm not going to show it now, and you can look at it there. So some terminologies, we got to talk about kinetics, and I'm going to go kind of quickly because it's going to be kind of a long video, so please hit pause to write this stuff down. Kinetics is how fast a reaction will occur. And something that we're not going to talk about our level of chemistry, but if you go on in chemistry, you have to talk about the reaction mechanism, all right, and what happens, intermediates before it gets to the final products. We just kind of briefly intro it. We don't really go into it. Another thing is rate, all right, how fast something occurs. All right, it's similar to speed, but it's kind of the inverse of speed. Like the higher the rate, the faster it occurs. So, or inverse of time, I should say. All right, so it's kind of a different way of looking at it, but it's not bad. It works out really well. All right, kinetics. All right, so reactions and their mechanisms. All right, so that's what we already said. All right, so a reaction is the breaking and forming new bonds. All right, or reforming bonds. All right, to make entirely new compounds and products. So you're going to break bonds. You have to first break bonds if they're not already broken, then they have to form new bonds. Remember, breaking bonds is endothermic. And then reforming new bonds is exothermic. Now, to figure out if an overall reaction is endo or exothermic, you have to look at the overall amount of energy required to break it, then how much energy is released when you form it. So the net difference between those two will determine if the overall reaction is endothermic or exothermic. So we're actually going to be dealing with a little bit of math in the beginning part of this and the kinetic side of it. And then we get to the equilibrium. Kinetics is probably going to take 2 classes, and then equilibrium probably equally as well, 2 or 3 classes. All right. There's a great lab that I have no idea how to do at distance learning. It's probably one of the most the favorite labs that kids do. I'm trying to figure out what I'm going to do with that. I don't know. Anyways, so it's breaking bonds and reforming bonds, and seeing the overall reaction that is gained or lost as a result of that. Remember, endothermic is absorbing energy, exothermic is giving off energy. Reaction mechanism, real quick, step-by-step process to get from A to B. All right, you put ingredients in a bowl, mix it up, you bake it, and you make a cake. All right, your initial ingredients turn into your final product. What do you have to do in between there? That's kind of the reaction mechanism. All right, you have to crack the egg. You have to measure out the ingredients. You have to mix them up correctly. You have to grease the pan. You have to cook it in the oven. You have to let it cool down, and all those things. Those are the steps or the mechanism that's involved in making a cake. All right, but the overall people would see that didn't do that would just see maybe what you started with, or they recognize what you started with, and they know what the final product was. All right, so I equate that to making a recipe. That's why we talk about cakes. All right, you can't, if you're gonna make a cake, you can't omit cracking the egg open. All right, or you can't omit the water, or you can't omit mixing it up. You have to do all the steps, and to do it correctly, you have to do the steps in the proper order. All right, so you can't change the order of it. You can't, mix them up, bake it, and then add the eggs. All right, that doesn't make sense, and I know that's illogical for you to understand that, but that's something like in chemistry that someone would try to do something like that. And you can't omit any of the reactants. You still have to have all of the reactants there. You have to have them mixed and introduced to each other in the proper order, and then they will turn into the products that you expect. If you don't do those correctly, then you're not going to get the expected products. All right, so what I want you to do, these are all reactions, and once again, with video, I'm not going to leave it up here long, so just tell me if they would be slow or fast. So you're looking at these things. You've got rusting, Alka-Seltzer in water, if you've ever seen it. That's that plop, plop, fizz, fizz stuff that bubbles, the little tablets you put in water and they bubble. It's used for upset stomachs. Styrofoam decomposing, weathering of rocks, and bleaching of fabric. All right, so slow or fast, relatively speaking. Rusting, is that going to be a fast or slow process? Rusting is a relatively slow process. You throw a piece of metal into water, it's not going to rust instantaneously. It's going to take time, depending on what metal it is. Some takes a little bit of time, some takes a lot of bit of time. All right, Alka-Seltzer in water, as soon as it hits the water, it's going to start bubbling, so that is a fast reaction. Styrofoam decomposing hardly ever happens, so that styrofoam is a very slow process. Weathering of rocks is another slow process. It's not as slow as styrofoam decomposing, but it's something that does take some time. Bleaching of fabric, if you've ever done that intentionally or unintentionally, it does happen pretty quickly or almost instantaneously, so that is a fast reaction. All right, what determines the rate of a reaction or how fast it goes? All right, it's the number of steps. All right, however many steps, to make, let's see, to make macaroni and cheese, Kraft mac and cheese. You have to boil water, you have to cook the pasta, and then you mix the ingredients and you go. All right, if you're making pizza, if you're making the dough, you have to make the dough, you have to let it set, you have to stretch it out, let it set, you have to stretch it out, then you put the ingredients on it and you bake it. So the number of steps in making a pizza are inherently more than it is to make macaroni and cheese, so it takes a lot longer to make pizza than it does macaroni and cheese. All right, there's what's called the rate determining step, and this is where I'm going to go back to the baking of a cake. Rate determining step is the step that takes the longest. All right, so when you bake a cake, what step takes the longest, or what instruction takes the longest? All right, I think everybody would know baking the actual cake would be the longest process, so that's the rate determining step. That's ultimately what's going to be used to determine how fast or slow your reaction occurs at. Can you speed that up? Can you speed up baking? Well, yeah, you can. You can make little cupcakes versus a cake. All right, you can increase the temperature of your oven to a certain point, but that'll change the texture in some ways, so you got to be careful with that. So these are things that you can play with to see if you can still get the same possible result. All right, but this is the most important factor in determining how fast it'll occur. All right, A plus B plus C makes ABC. So in this case, it's shown there's, in this direct diagram here, it shows there's two steps. And we're gonna see these roller coaster lines. All right, think of a skateboard person, roller coaster person. You have your reactants A and B. They're gonna react, and this is a relatively slow process because it's a big hill. All right, and a relatively slow process, and A and B are gonna form product AB. So they join together somehow, some way. We don't really care what it is, just that they did. All right, and then the second step of the reaction is A and B are then going to react with C. Now, comparatively speaking, from A and B making AB, AB plus C is a much shorter process. Think if you're riding a bike up the hill. All right, this hill would take a lot longer to get up. All right, so how much time or energy it would take to get up is the energy required to get it started. So since this hill is much smaller than this first hill, all right, this is a quicker reaction, and then you make your final products A, B, C. All right, when you look overall where you start and finish, you got A plus B plus C is going to make A, B, C. So you don't see these individual steps. Just like when you eat a cake, you don't see the individual steps that went into making that. All right, so that's the rate of the reaction. All right, tall hill is slower, Short hill is faster. All right, collision theory. You can't react if you don't collide. You need what's called proper orientation. I make you guys act like bumper cars in class when we do this. If you guys have ever been on bumper cars, and what you try to do in bumper cars, you're trying to ram into another person. You're trying to inflict the most, I don't want to say pain, it's not really pain in bumper cars, discomfort or jarring activity as possible. The best way to do that would be a head-on collision, right? Okay, so what this graph is talking about is number of bumper cars. All right, you can see that the number of collisions, all right, it gets, or the kinetic energy they have, how fast they're moving. As you get more molecules, all right, it goes up, and then you get to a point where too many cars get in there and they can't really move, so they can't really collide. All right, we'll talk about this graph later on in something else. But bumper cars, think about what's the most ideal way to cause a crash. You want to ram head on. What do they try to prevent you to doing in bumper cars? Going head on, because they make you go in one direction. All right, so you need what's called proper collisions. All right, you can't glance off it. Another way you can think of it is making, if you've ever hit something with a car, hopefully you haven't. There are car collisions that won't cause damage. There are car collisions that will cause damage. All right, you can be pulling into a parking lot, moving really, 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 really slow, and you just tap the bumper of a car in front of you or behind you. Probably won't cause damage if you're going really, really, really slow. Now you can come into that same spot and ram into that car at 20 miles an hour. That's going to cause damage. All right. What would cause the most damage between two cars? A head-on collision where both cars are moving at each other. All right, so that, but you can also glance off the sides, and there's all different kinds of scenarios. We go into some of them in class. I'm not going to take up your time with them right now. So here we go. We got A squared. We got diatomic A and diatomic B are going to collide to make two ABs. So if we look here, here's AA and here's BB. If these things are going to move together towards each other, if they're going to move and collide this way, are all the A's going to collide with all the B's? No. So you're just going to get these two colliding, which could make an AB particle if it's moving fast enough, if it overcomes what's called the activation energy. But is this particle ever going to touch that particle? No shot. So they're not going to make a product. So that doesn't work real well. What about this way? All right, here's your AA, here's your BB. This thing comes in, maybe it rams into there, maybe it rams in down here, maybe it rams into the middle. Doesn't really matter. All right. If it's going fast enough, if these things are colliding fast enough, they're going to react. And if they're moving fast enough, they will collide and they will form the product AB. But in this orientation, if they're coming in this orientation, this particle is going to hit one of these things here, all right, and only going to make one product particle. Here, now, if these are both moving fast enough and they move right at each other, both particles will collide with each other. If they're moving fast enough, they will both turn into products. So this is what we call proper orientation. You want these things oriented correctly. You don't want two cars going away from each other. All right, you don't want two cars, going next to each other in the same direction. They can still collide with each other. All right, but it's not going to, you're just kind of bumping the person. You're not going to inflict as much damage as possible on that other person. Speed. Speed is critical. How fast particles are moving. All right, how do we make the particles speed up? We increase the temperature. All right, they have to overcome what's called an activation energy. All right, that's the minimum amount of energy needed to get it going. All right, we abbreviate activation energy as E sub A. And I'm really upset at myself. This morning I went to grab matches to show you this. All right, if you've ever seen somebody do matches, you cannot light them, even though you strike the match on the plate, on the box. And that's because they don't have enough activation energy. So you got to give it a minimum amount of energy to get it started. All right. So not that I'm telling you to play with matches, but if you've ever tried to light a match and it doesn't light multiple times, you're not giving it enough energy, or you're not giving it the proper angle or orientation. So matches work really, really well, for an example, for collision theory. All right, collision theory, for something to react, they must collide, and they must collide in the proper orientation and with the correct amount of energy. All right, so successful collisions only occur when particles collide with the correct orientation. So they got to be moving kind of directly at each other in most cases, and they must collide with enough speed. So that's kind of, that's the sum up collision theory. You need to collide. You need to collide with the greatest force possible. All right, and if they do collide with the greatest force possible, then they will react to form products. That's kind of what that's saying. That's all the collision theory is saying. You just kind of inflict as much damage on another particle as possible. We equate it to bumper cars, whatever. All right, but ultimately it's the same thing. If you've ever been in a car accident, you know, depending on how fast you're going, the amount of force that's there. Okay, not going to show you this car accident without being in class to explain it. So it's a pretty nasty one though. If we do come back to school, remind me about that, and I will show that to you, and we'll talk about it. I just don't want to do it just to assign it to you because it's not a good car crash to see. All right, what is activation energy? Activation energy is, we abbreviate E sub A. All right, is the energy needed to start a reaction. All right, whatever that energy is. All right, so a match will not light on its own. It's got to have mechanical energy, so it'll light. All right, heat of reaction, delta H. So now we're going to get into abbreviations and interpreting graphs. Delta H, delta means change in. If you guys remember, like delta T or delta Y over delta X. We've dealt with delta before. You've dealt with delta in math. It's the Greek letter. It's the difference between the potential energy of the reactants and the potential energy of the products. Just like we kind of taught before, delta H is always calculated as the products minus the reactants. So delta H, this is a formula you're going to want to write down. It's not a real hard formula, but delta H is always the products minus the reactants. This is important because we can, this negative number here, doing it in this order, we can get a negative or a positive number, and being negative or positive tells us some information. So you have to do this in the correct order. You have to have the correct number, and you have to subtract it correctly. So delta H is the heat of the products minus the heat of the reactants. Okay? So here we go. So here we're going to get into a graph, and this is kind of where we're going to end up with these graphs. You know, we're going to introduce these. These are called potential energy diagrams. I would draw it fairly big, half sheet, full sheet of paper. All right. If you're using the packet page, I don't know, it's almost a half a sheet of paper. So down here at the time, we can have reaction mechanism, we can have the rate. Over here, we can have potential energy. All right, it's never temperature, it's potential energy. All right, and you're gonna draw that in. Now, notice these kind of lighter, thinner lines. These are just reference point lines. All right, I just do those to give you reference points on here. All right, but basically you have a hill. You have to get up the hill. And once you get up to the hill, think of this like a skateboarder. I don't know if I can draw a skateboarder. Let's see if I can. This is gonna, so you got a little person. So you got, here we go. If you can see this, ooh, that's not a very good straight line. I'll try to top it up, raise it up here. And then we're gonna put a person on this. So this person's on the skateboard. So think about that. So, you know, you can think about it as a skateboarder, you can think about a roller coaster person, whatever, you know. But the skateboard person starts down here and they have to get up here. So if you got the skateboard person, you're gonna make me draw another one. This is kind of funny. All right, tough draw. When you're a left-handed person, using a mouse to draw is a challenge for you with your opposite hand. All right, yeah, that's not a great person, but it works. Okay, so we start here. The skateboarder, bike rider, roller coaster's got to get up to this point in time. Now, as soon as that skateboard person gets just past this hill, just on the downhill slope, is there any way to stop? Last time I checked, skateboards don't have brakes, so there's no way to stop. So they're going to go until they either fall or they get down to this part and all their energy is used up. So on this graph, what we talk about, this is where you start, this is where you finish, if you're going in what's called the forward direction. All right, we'll talk maybe at the end about reverse reactions. I don't quickly just intro it. It's not really that hard. But anyways, potential energy, and we can put numbers on this in terms of joules or kilojoules or, you know, what 1, 2s, and 3s, whatever. All right. So on here, I've got to try to get to my, here we go. So this line right here, whether it's drawn here or over here, just from that line down to this line, the difference in height between where you start and the bottom of the axes, that is called the heat of the reactants, or the potential energy of the reactants. PE means potential energy. It's the potential to be able to do anything. So basically where you start, or the height of the hill, where you start is potential energy of the reactants. All right, we're kind of going a little bit of a logical order. Where we finish, so the height of the hill of the line where you finish, so down here, the flat line down here, where you finish, that's potential energy of the products. So you got the reactants, you got the products. Now, I draw it here underlined to make it logical sense. You could also put potential energy of the products over here. All right, it's not where it is laterally or side by side. it's the height of it. So potential energy of the products is here. This is also the potential energy of the products. We could draw it over here, this height right here, whatever the value is. We could put numbers here. All right, I don't think I put numbers on this slide. So if we go 1, 2, 3, just simple. All right, potential energy of the products is 1. Potential energy of the reactants in this case is 2. All right, 2, in this case, kilojoules or joules, whatever. It doesn't matter the unit. We're not really worried about that. All right, next thing. Okay, so here, this is the difference between the products and the reactants. All right, so the products is here, the reactants is here. The difference between that. All right, it is the products, which is 1, the reactants, which is 2. So 1 minus 2 is -1. That is delta H. Sorry, I have to go down here to get, I think I have to go down here. That is delta H, or the heat of the reaction. In this case here, delta H is calculated as 1 minus 2. 1 minus 2 equals what? -1. That negative is super important for this graph, and we'll talk about that in a second. All right, so that's a -1 for delta H. Let's see, what else do we have to identify? We have to identify this line right here. This is the height of the difference between where we start and to the top of the hill. So where we start at the top of the hill is called activation energy. All right, EA. Remember, we're going to use that abbreviation because I'm not going to write out the word activation energy. So the energy needed to get to the top of the hill. The energy needed to get to the top of the roller coaster. Getting up that that first hill. That's the activation energy. Once you get to the top of the hill, you're going to go and you're going to get to the products. All right, what else do we need to know on this graph? All right, this is this yellow line, and I drew it yellow so we can see it differently. That's what's called the activated complex. We haven't introduced what the activated complex is. I'll talk about that next class, but just that's more of a kind of a jumping ahead game. All right, so that's the active potential energy of the activated complex. And once again, I'm going quick on this, try to limit the size of the video, and you can pause to write things down. Activated complex is when the reactants collide in proper orientation. It's kind of like the cake baking in the oven. Not going to worry too much about the activated complex today. All right, basically bonds are breaking and forming during that process. All right, it's momentary, and it only lasts a moment. So like literally once the skateboarder gets there, it's going down the hill. There's no pause at the top like they do in some roller coasters these days. All right, quickly moves to products, yes. All right, so here we go. So now you have that same backbone of that graph. You can keep your graph there. You can see this kind of grayed out area. We're going to introduce one more thing. All right, this dotted line. And it's always drawn with a dotted line. I'm not sure why. If you notice, this lowers the height of the hill. All right, this lowers the height of the hill. And if you lower the height of the hill, that means you're going to reduce your activation energy. All right, if you reduce the activation energy, you're going to make the reaction occur quicker. This shows the mechanism for what's called a catalyst. You guys may or may not have heard of a catalyst before. All right, catalyst speeds up the reaction without actually changing the reaction. Hold on, I gotta let my dog out. All right, so a catalyst will speed up a reaction without changing the reaction other than reducing the amount of energy needed to get it started. So that's what that is. Catalyst compound which lowers activation energy. It's not permanently changed. All right, it can be reused. You probably learned of a catalyst in living environment in terms of enzymes. If you haven't taken living environment, you will next year. All right, but notice the catalyst does not change the delta H. The delta H value still stays the same. All right, I'm gonna keep going. You guys can pause to write things down. All right, so here we go. So this is kind of what you're gonna be doing for homework tonight, so I wanna kind of see here. All right, so here we go. So now this graph here, all right, because you started high and finished low, remember I had a negative delta H, this is an exothermic graph. It gives off energy. It's got a negative delta H. Does this graph have the same general shape? No, it does not. This one goes uphill. So this one's going to absorb energy, which means it's endothermic. This is an endothermic graph. Okay. So values. So what values can we see? What do these letters A, B, and C represent? Now up here at the top of the hill, all the way down to the bottom is the activated complex, which we're not going to deal with on here. A, in this case, represents activation energy. All right, it's the energy, it's the difference from where you start to the top of the hill. On this graph, because there's numbers here, activation energy would be 400 minus 100, which would be 300 joules, kilojoules. They didn't give us units for that. B is kind of one of those pain in the neck ones. It's talking about a reverse reaction. It's called the reverse activation energy. It's the height of where you'd start to finish if you went from the products to the reactants. So B is kind of a confusing one on here. C is the difference between the products and the reactants. It's delta H. All right, delta H, products, which is 300, reactants, which is 100, 300 minus 100 is 200. All right, so the delta H in this case would be positive 200. Positive delta H's are endothermic. All right, so delta H is the products minus reactants. So in this case, the products is 300 minus 100. So you're going to get 200. That positive number means it's endothermic, which means it's going uphill. All right, so uphill graphs are endothermic, downhill graphs are exothermic, downhill graphs are negative delta H's, uphill graphs are positive delta H's. All right, so for endothermic, delta H is always positive. All right, here we go. We're going to quickly do an exothermic graph. So here's an exothermic graph. I threw some numbers up here. All right, A represents the heat of the reactants. What is the value for heat of reactants in this graph? Heat value is 125. All right, B represents the difference from where you start to the top of the hill. That is the activation energy. So B is activation energy. What is the value for activation energy? 145 minus 125, which is 20. All right, C, what is C? C goes from the bottom all the way up to the top of the hill. That's the activated complex. The value for the activated complex in this particular graph is 145. And then D is the value of the products or where you finish, which is 0 to 50. So the value of the products is 50. Delta H for this graph. How do you figure out delta H? Delta H is 50. Well, I'm going to give you a second to figure that out. All right, so the heat of the products in this case is 50. The heat of the reactants is 125. So 50 minus 125 is negative 75. That negative is important. That negative tells us it's exothermic. All right, so remember, endothermics have positive delta H's, exothermics have negative delta H's. All right, exothermic is always negative for delta H. I'm going to end there. These things right here, the page 7, I think, is going to be graded on correctness, not completeness, so make sure you do it correctly. When you do that, have fun with your Ed puzzle. It's quick today. All right, have a good day.